Good evening. I'm sorry for being a bit late. So, Sasha, welcome. We are going to listen to Sasha Mikhailov from the Leeds University. And well, I again kindly ask everyone to switch off, except for Sasha, their microphones. Sasha, let's begin.
Well, actually, I want to say a few words about Sergei Natanzon, who passed away yesterday having COVID, and that is a great loss for our community. I really, like this person, and we discussed many things with him, and even I had some plans to work together. That is sad news for all of us. So we should.
Yes, correct. I knew Serежа for years because we were mates at the university. We were at the same, we studied for 5 years in Mehmat, and then, contacted for many years. So it's a great loss and personal, and he was a brilliant mathematician. It's a pity.
Right. Okay, so I think I will begin my talk, and let me switch to slides. Today I'm going to talk about a very simple idea which is miraculously works, and moreover I try to talk to experts in this area, and it looks like this idea is kind of obvious, but have not been really explored in the area. And the idea is how the question what I want to set, how we quantize dynamical systems. And there are many approaches, and some very famous, like geometric quantization, deformation quantization. And this problem starts from classical works of Heisenberg and Dirac, and through the centuries, a whole 100 years, and actually it's quite dangerous to do anything in this area, as you understand. But I will show you how things works, and if you give me a good reference where people study this way, I will be happy. But up to now, I don't know anything, and it works, and I think if will be applied further. So what I'm going to discuss is first I will start to compare pictures in classical mechanics, quantum mechanics, and I will define free associative mechanics and reduce, and the free associative mechanics will be on free algebras. So the idea is not to start from classical equations on commutative setup like everybody does, but start from the most non-commutative case, from the case of equation on free algebras, and then to reduce the problem of quantization to the problem to find some proper ideals in these algebras, and reducing the system on a quotient algebra. That's the basic idea. And then I will illustrate this method on rather non-trivial examples of Volterra and Bogayevlensky systems, and will show some features of this. And the most recent thing, which have not even been ever published, I applied these ideas to some dynamical systems on free algebras, on integrable systems, which we studied maybe 20 years ago with Volodya Sokolov, and also other works of classification of integrable systems on dynamical system on free algebras. So that is a plan. So you are welcome to interrupt me at any point of my talk and ask questions, so I will be happy to answer. And I will try to be as simple as possible, so even students first or second year should be able to follow me. So let's start from Newton equation, and with 1 degree of freedom. That's what we study in the first year of university, probably. And we know that Newton equation with 1 degree of freedom is an integrable system because there is a first integral, which is called the Hamiltonian, this one, and that is the first integral, a constant of motion, and we can write equation in Hamiltonian setup and using the Poisson brackets, standard Poisson brackets between P and Q is 1, and so that is the classical stuff. And this equation, everything lives in a phase space with coordinates P and Q, and any function in this phase space can be differentiated according to this equation using the Poisson bracket with the Hamiltonian. So that is a standard setup. Everybody knows. Then in the second year, we study quantum mechanics, and that picture probably belongs to Heisenberg, and there later a little bit clarified by Dirac. In this case, we live in a space with coordinates P and Q, and these coordinates are not commutative. There are some commutation relations that if you commute P and Q, the result is IH. The constant Planck constants, and I is a square root of -1. In this case, equations also can be written in the same exactly form, and H is the constant of motion. So if you differentiate H according to this equation, but you should remember that P and Q not commute, so you have to be careful in the ordering of terms, but you will still find that the result is 0. And when Heisenberg discovered in his paper in the year 1925, and that also mentioned in the paper of Dirac, that Heisenberg write, oh, I am in the right way. Look, we find that H is a constant of motion even if the variables not commute. So everything works like the same. The only thing that Poisson brackets now replaced by commutators, and if you commute our H, the Hamiltonian and variable Q, and use the commutation relation, you will reproduce equation for Qt and a second equation for Pt. And any polynomial function in variables P and Q can be differentiated according to this equation. It's a just commutator with H, with a Hamiltonian, and with up to this constant I divided by H. And we live in the actually, this is, this algebra can be seen as a quotient of free algebra with variables P and Q, free non-commutative associative algebra, quotient over the ideal, two-sided ideal generated by the commutation relation. Let's go further. Now what I want to do, I want to consider equations on a free associative algebras. So that will be, well, you may not consider as a kind of interpretation to mechanics, etc. Although I think if you think a little bit, maybe it has some meaning. But for me, there will be some starting point. Let's consider equations on free associative algebra. So P and Q, two non-commutative variables, and we generate algebra over C. So any polynomials, any words in P and Q and linear combination with C are elements of our algebra. And this algebra equipped by derivation, so it's just from derivation should be linear and also obey the Leibniz rule for any elements of algebra. And then we can define Newton equation. If you're not really familiar with free algebra, you can mean, for instance, that A and B are matrices, square matrices of arbitrary size. Well, the size is not fixed, so it should be true for any, because if it's a fixed size, it's not a free algebra. But it should be true for any size like that. So you can think of this equation as equation on matrices, for instance. So we have these two equations. And P and Q are functions of t. This equation have immediately, we can spot one first integral, one constant of motion, which is a commutator of P and Q. If you commute P and Q and take derivations with respect to t, apply the Leibniz rule and apply our equation here, you will immediately get 0. So the commutator is a good thing, you know, that is okay, first integral. It's element of algebra, and that is a constant of motion. But if you try to do the same with the Hamiltonian, and Hamiltonian you can, or Hamiltonian function, or whatever, what used to be in quantum mechanics and in classical mechanics to be a constant of motion, you will fail to find a constant of motion. Let's consider example. If you take, for instance, force, well, if force is not linear, of course. If force is linear, it's still first integral. So if you take force quadratic in Q, like here, and then potential is cubic, you can check directly by applying Leibniz rule and our equation, the derivative of H is not a zero, but some combination of P and Q. Well, then people say that let's consider not H is not element of algebra. Let's we take trace of H. If you take trace of H and can swap cyclically variables in this expression, of course you will get zero, and the trace everything zero, and you can define trace on free algebra like equivalence relation up to cyclic permutations of terms in a monomial. Then it will be a first integral. Then it will be a constant of motion. But I don't want to define any traces, any these kind of structures. What I want to tell you that is not, I mean, a constant of motion as it is given. You need something else. You need to define some functionals or whatever, some equivalence relations. But these equations still have symmetries, and that is quite interesting. That in commutative case, we know that any symmetry, time-independent symmetry of Newton equation should be Newton equation itself proportional. We don't have any other symmetries. Here you can construct the next symmetry of equation. Look, this flow will commute with the Newton equation, and that is not proportional. It's just a different flow. You can construct more.
Sasha, I'm sorry. What do you mean here by higher symmetries?
Higher symmetry means, look, we have equation, the Newton equation is a polynomial, for instance, is a P here and here is Q square. Yeah. Now I will have polynomial of higher degree in our...
in the sense of degree, okay.
Higher degree, and you can make high and high degree, and there are infinitely many.
Yeah, thank you.
Right. If you go back to commutative case, now you can forget, now we say, okay, I will allow myself to swap all the variables like in commutative case, then you will immediately find out that your new symmetry is not new, it's proportional to the Newton equation, and the coefficient of proportionality is H, which is a constant, because we need to extend the field of constants by constants of motion, and our H is a constant of motion, right? So it's not new in the commutative case, but it is new in the free algebra. Now, what we can do to go from free algebra to quantum or to commutative? Well, let's first look on the structure of our free algebra. What is a free algebra? In this case, we have free algebra generated by two letters, P and Q, and that we can define a set of monomials. Monomials is any word written in P and Q with some repetitions, because P, I, and we cannot swap these terms, they're all different. So we have, and the number of, if we fix the degree, and the degree is a sum of all exponents, then the number of terms of degree n will grow as 2 power n, exponentially will grow. If you go to a commutative case, and commutative algebra can be seen as a quotient of our free algebra over the commutator of P and Q, over two-sided ideal generated by commutator, then, or in a quantum case where the quantum algebra, quantized algebra, is a quotient of our free algebra over ideal generated by this polynomial, then first of all, in both these cases, the algebra has an additive basis of standard monomials. By standard monomials, I mean monomials in which P stands in front of Q in some power. We can always swap and move P in front and the Q to behind. So we can the basis of this algebra, of these two algebras, is an additive basis, and it's exactly as a growing exactly as a basis as an algebra of polynomials. Or people say that is a Poincaré-Bergov-Witt type algebra. So the grows exactly as algebra of polynomials of two letters. And any element of our algebra can be uniquely represented by a polynomial in which every monomial is in the standard form, in this standard ordered form. So that's what I want to point out. Now I give some kind of definition. It's not really well, I mean, 100% proved definition. I will tell you why I think so. But today my talk is based on this definition. But now I think we should think a little bit more and extend this setup. So the first fact is that if you have any associative algebra, then you can represent it by a quotient of a free algebra over a proper or some certain two-sided ideal. So in quantum case, we already seen that. So that what I want to do, I want to study ideals of our associative algebra. What requirement on these ideals I want to impose? The first requirement, which is not really the first requirement, which is not, I think that can be a little bit modified later on, that the quotient algebra has additive basis of standard monomials. That means it grows exactly as algebra of polynomials. Second, or maybe not exactly, but has additive basis of standard monomials. So we can swap any two elements in this algebra. And the second, the most important requirement is that our derivation, because we want to quantize a certain system defined on the free algebra, so we do have a derivation on free algebra, that this ideal should be invariant with respect to this derivation. And that enable us to induce this kind of derivation, induces derivation on the quotient algebra and enable us to reduce the system to the quotient algebra. That's the second requirement. And these ideals satisfying these properties I would call quantization ideals, and the quotient algebra is a quantized algebra for our dynamics, because dynamics already here. Look, we have this dt, and dt is dynamic. So it's not just abstract quantization, it's quantization of a certain dynamical system. Let's go back to our Newton equation, and we consider our Newton equation on the free algebra. Now, as a candidate of ideal, I don't know what ideal I can take. I want to satisfy these two properties. The property Q1, well, I will give some sufficient condition, could be generalized, and we will discuss it probably later, how to generalize it. For instance, if we consider an ideal generated by one polynomial, it will obviously satisfy condition Q1, because in this ideal generated, we enable us to swap P and Q and make some ordered a normal monomial from any monomial. I mean, from any monomial we get a polynomial with a normal ordering in every monomial. So up to a few terms, and so that is obviously satisfy Q1. And the two-sided ideal is just a set of elements G multiplied by AI and BI, where AI, BI, any elements of our algebra. And so that is a sum of these elements. That is the structure of the whole ideal, two-sided ideal, which generated by this polynomial G. Now I want to raise a question. So Q1 is satisfied. What we need to do to satisfy condition Q2? That means if we differentiate this ideal with respect to our dynamics, and our dynamics is a Q dot equal P. Let me do it a different way. Q dot equal P, and P dot equal Q squared. So we have dynamic, and that P and Q not commute. So if we differentiate with this dynamic, this ideal, so that means actually it is sufficient to differentiate J, because if you differentiate A, you are obviously an ideal, you have still G here. So need to differentiate G. So if the condition that our ideal is invariant is can be reduced to the fact that derivative of G in T is invariant, is in the ideal. If you differentiate and substitute dot by P, so if you differentiate P dot is Q, so P dot is Q squared, or F of Q, so F of Q here is F of Q. F of Q, it's one in our example was Q squared. So you will get, basically will get this expression. Then you look what, okay, our ideal enable us to put everything in normal order, in the order, but nothing to order here because everything is ordered already. And P squared will be terms vanishing if omega, only if omega is equal to 1. If omega is equal to 1, then so the P terms vanishing is if omega is 1. If omega is 1, then the second term is vanishing. Then you look here and you say that, okay, alpha and beta should be also equal to 0, because that's the only way this derivative is in the ideal. And you immediately get to the Heisenberg commutation relation. So the only ideal of this form, which is compatible with the dynamics, is a Heisenberg relation. Of course, gamma should be IH, and that can be, you need some stipulation about reality arguments, reality conditions, that P and Q should have some the observable, some physics, that real eigenvalues, so P and Q can be represented by some Hermitian matrices or operators, and then gamma should be I multiplied by a constant. But we are not going so far. I just want to show that we really find the ideal, we really find the quantization. Now, let's look on the let's look on the associative algebras of n variables. And if you take 3 algebras of n variables, what kind of ideals we can consider? We can consider we can consider several ideals. So we want that these free algebras can be written in standard monomials in these free algebras when we have all variables, all indices, lower indices are ordered. So that is a standard monomials. So what we want to have a quotient algebra such that they has additive basis with ordered monomials. And that kind of algebras being studied actually, and there is an excellent thesis of Victor Lewandowski from Kaiserslautern. He works with the same group as Fitzer, probably singular system. So he was responsible for non-commutative part of this singular system. And his thesis was actually devoted to G algebras. So non-commutative algebras in which you can introduce Gröbner basis and everything works. And in particular, you have this, and he calls it G algebras. And these G algebras is a quotient of a free algebra over ideals generated by expressions like here, generated by these polynomials, where omega ij are constants, non-zero constants, and psi ij are polynomials, are elements of our algebra, and they have some ordering in this algebra, some linear ordering in monomial ordering. So the leading monomial of this psi should be less than psi ji and psi ji less than. So that enable to play all these games. And one extra condition here, which actually guarantee that the multiplication rule given by these polynomials, you can consider it as a multiplication rule for xi, how to multiply by xj, and expressed in a normal form, should satisfy one identity, which follows from the associativity of this multiplication. And this algebra has a Poincare-Bergov with basis and that everything, so they satisfy Q1. I don't go beyond that. I don't know actually general description of this kind of algebras, but that is the best what can be done at the moment, and well, at least according to my knowledge, and that's what I will use here. Now let's go to some examples, and as an example, I will consider the famous Volterra chain and Bogayevlensky N chain. What is a Volterra chain? It's a system, we will consider infinite and finite systems. This Volterra chain, I think in commutative case, the integrability of this Volterra chain was discovered by Sergei Monakov first, and then later by probably Flashka and Adler van Merbeke, and even later, and eventually it gets several names: Volterra chain and Langmuir chain, what Monakov called it, or nobody tell about. Bogayevlensky also discovered it, but eventually many people call Adler van Merbeke, although they did it much later. And Bogayevlensky find a generalization of this chain, also integrable system, where not so let's talk about the first one. Let's talk about this chain. It's not one equation, and how to understand this equation. We have a lattice Z, and we have a variable u on a lattice Z, which depends on variable t. So we have infinitely many equations, and we have infinitely many variables. And here we adopt a standard notation. So u is u at point nt. Like when we write differential equation, we never write that u of x, x of t derivative in t. We just write x. We forget about argument t and point t. In this case, we also will write u. Or u will be identified the same as u naught. If we shift, so you consider value of this function at the point n plus k, we will write the index k down. So that is the shifted values. So we have this equation, and we have infinitely many, because we can shift this equation to the left, to the right. So you can basically, what you can write, you should understand this equation as a u n dt equal un plus 1, un minus un minus 1, and n in z. So that is infinitely many equations. This equation has lots of structure, Lax pair, integrals of motions, symmetry, infinitely many symmetries, Hamiltonian structure, even multi-Hamiltonian structure. So lots of things known about this equation. And the other equation is the same, but you have not only shift on one to one, on here is a shift not only on one position, but up to n positions to the left and up to n position to the right. So it's a much longer equation. And for any n, also everything is known. Also, the system has Lax pair, integrable, etc. So, but that was known in commutative case. In non-commutative case, when u and u1 and uk and us not commute, but just no commutation relations, just elements of some free algebra, I think the first this thing was discovered by Oleg Bogayevlensky. This equation, Bogayevlensky equation, also been studied by Ito.
I'm sorry. So this S, this shift, it in a sense plays the role of GDEq. Yes. So it is a discretization of.
Yes, you can look at the discretization, but I don't want to. This differential equation is a little bit trickier. We can discuss it later. It's just a lattice equation, like for the lattice. And that is a proper discretization, for instance, of Korteweg-de Vries equation. You can find from both these equations, you can go to Korteweg-de Vries by continuous limit if you assume that NH is X and H goes to 0.
Mm-hmm.
So you can find famous Korteweg-de Vries equation. You can find many equations from here as a continuous limit, because there are plenty of continuous limits. But I don't want to go this way. I want to go my way about quantization, and I want to quantize these systems. In order to quantize, I have to define, so that my idea is not to go from continuous equation and study their Poisson structure, the Poisson brackets, etc., and then deform everything to commutators. No, I want to go opposite way. I want to go to free algebra, find the equation on free algebra, then write an ideal and try to satisfy the conditions which I formulated in the previous slides. That ideal is invariant with respect to dynamics, and in this way I will find the quantization that I want to show. So as equation on free algebra, it was found as an integrable system by Oleg Bagaevlensky, and there is a review in Russian Mathematical Surveys, I think 1985 or something like around that year, when he found Lax pairs and plenty of these kind of equations. And here the ordering is important. Look, U1 stands in front of U, and U minus 1 stands on the other side. If you swap in one term, it will not be integrable. It will not be good equation. So that the ordering here is important. And having these equations and this lattice on this lattice, we also have a natural automorphism of our algebra. So we have free algebra generated by all these variables of infinite number of elements. Of course, every element of algebra is some polynomial which depends only on a finite number, but we don't know what number of variables. So it's a standard thing. And on this algebra, there is automorphism. Namely, we can shift the index. We can replace UK by UK plus 1 for every k. And that is automorphism of the algebra, obviously. And it's, you can shift it many times, inverse. And these equations, the systems 1, they both invariant with respect to this shift, because it's an infinite system. So our derivation dt in this equation commutes with this shift. And such derivations people usually call evolutionary derivations, which commute with the shift. So, our algebra with a shift, equipped with a shift with automorphism, in this case of infinite order, is a difference algebra. Right. Is any question about the setup of these equations? And I don't know what this, I do seminar with this seminar for the first time. I don't know what people really discuss, probably. No question.
I think it's clear.
It's clear. Good. Yeah. Good. I like to be clear. Right. Now I will set a question. Now I want to define it was on free algebra. Now I want to set up an ideal, and I want to find a condition to the ideal such that the ideal is invariant with respect to the dynamics of these equations. So basically, well, I will start with some particular type of the most simple thing which works. Then we probably can discuss how it can be generalized and why I don't start with a more general. First of all, when we start with a simple thing, everybody can follow and everything is transparent. If I start to introduce lots of notations, then everybody will be lost. And then eventually it will be shown that this was not necessary. So let's consider the ideal, like maybe you discuss in your seminar quantum plane or quantum torus. That is when variables not commute, but when you swap two variables, they gain some coefficient, some number. And this number is non-zero. So I say that omega is non-zero. And this number may depend on P and Q, on what elements we swap. So that is I want to define this ideal Of course, it's infinitely many polynomials and infinitely many numbers, but we will see that we will find all of them. So it is sufficient for ordering to assume that P is bigger than Q. So I always swap using this relation. I always swap elements. I always order element monomial such that the well, it's written probably in opposite direction. P should be opposite. So E first should be biggest, then smaller, 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 smaller. So in that should be in this way. That should be in this way. Sorry, but it does not matter. You know, it's just a convention. I mean, I want to be consistent with this formula. So every monomial using this ideal, I can swap elements and order any monomial and put the highest shift on the left and lowest shift on the right, and only intermediate is here. So the axiom Q1 that our quotient algebra will be of that type with the normal monomials is satisfied. Now the second question is not as trivial as that, and I ask, okay, is it now I have dynamic, and dynamics is our equations, these equations. These equations, and I want to ask question, what conditions on omega follow from this equation from the requirement that the ideal is invariant with respect to dynamics. So we differentiate the ideal using the equation, and the result is a polynomial, and this polynomial belongs to the ideal. That's the question I said. And that's the answer. Answer can be computed very easily. Actually, if you do these computations, you can find this answer rather quickly. So the answer, if you take the Volterra equation itself, just take Volterra equation, we set our ideal, and we ask what implications from the fact that the ideal is invariant with respect to these dynamics, that this is a differential ideal. We differentiate and we are still in the ideal. And you can almost immediately convince yourself or prove the proposition that if you have un, let me write here, un plus 1, then they swap by some alpha un plus 1 un. And un equal un if n minus m more than 2. So the nearest neighbors swap on alpha. If the neighbors very far, they swap, they commute. First of all, you can see that in this case, we have a deformation of commutative case, because if alpha is 1, it is nothing but that all variables commute. If alpha is not 1, well, we have non-commutative algebra. And that is a quantization. Actually, this quantization has been known for years. In the school of Ludwig Faddeev, there was one member of the school, Volkov. I don't remember, I met him, and he solved the problem of quantization for the Volterra system using R matrix approach, you know, all this machinery of quantum inverse scattering, and he found this alpha, and he found this commutation relation, but that was a huge machinery to do the job. Here we get this result basically in few lines. We find, of course, if you want to solve really quantum problem, you need to go to representation theory, you find Hamiltonian, etc. So there are psi functions, wave functions, everything, you know, that will be a big job. But at least this first step becomes very, very trivial and obvious. Now, let's set a little bit different question. Look, Volterra equation is integrable. An integrable equation has infinitely many symmetries. a hierarchy of symmetries, infinite hierarchy of symmetries. And here is the first term in this hierarchy. So no, first, of course, Volterra equation itself. And that is a second, it's a symmetry of Volterra equation in the free algebra setting. So I don't swap any elements. You can differentiate this function in tau, in t, and this function you can differentiate. So you can do the following. You can say that you can differentiate u, t, u tau, you can differentiate in t, and you can check that that is ut differentiated u tau. Well, there are plenty of definitions of symmetry. That is one of reasonable definitions. So you will see that these equations are really, these two flows really commute, and that is a symmetry of each other, and you never ever swap any elements u, u1, u minus 1, etc. So it works on free algebra. Well, it follows from Lax pair, of course. It's nothing surprising. Everybody knows that, from paper of Bogayevlensky, for instance. Now I said the same question, but not for the equation, but for its symmetry. So what you expected, okay, you have equation quantized, what happens with the symmetry? If you set this question to the symmetry, then you will find two answers, surprisingly. One answer is the same as in the case of the Volterra. So the symmetry of Volterra equation admits the same quantization as the Volterra equation itself. It's not surprising. Well, and what everybody would expect. But what is not expected is that there is a second solution. And second solution is that there is a second ideal, a different ideal, which is not working for the Volterra equation. Namely, we have commutation relation that have minus 1 power n here, and the neighbors which far from each other, I mean more than one, the distance, they anti-commute rather than commute. So it is not a deformation of a commutative case. It's not a deformation of anti-commutative case. It's just a new ideal, a new quantization, which can be found in this way. Then you can naturally ask the question, what happens with the higher symmetries? And in my paper, there was a conjecture, because I checked several symmetries by just doing computations, but then I kind of invite one of my co-authors and the former student of Victor Katz, Sylvain Carpentier. He is now in New York in this Columbia University, I think has a postdoc, and we discuss the problem, and he brings some proof that every symmetry of the Volterra equation admits the same quantization as Volterra equation. But if you consider symmetries of odd order polynomials, and we have, so Volterra is an even order because it's second order in U, symmetry is cubic, next symmetry of order 4, then order 5, etc. So symmetries of odd order admit quantization B. So there are infinite sequence of equations. There is a new quantization. Nobody knows what quantization is about, and whether, I don't think it has been studied. Nobody at least tell me that this quantization will be found. And that cannot be found as a deformation of the commutative case, because it's not a deformation of the commutative case. Right, that is the first surprise. Let's go further. What is here? Here. Now, well, when we're talking about infinite lattices and the infinite algebras, it's everything is a little bit not comfortable. It's much better to talk about algebras with a finite number of generators, because it's much more known about these algebras, and everything kind of, we have better ground. No questions about convergence, formal series, formal sums, anything like that. So what we can do, these equations have this shift invariant, so we can consider periodic reductions. So we can consider that after m steps we get the same value. So instead of infinite chain, we have a finite chain of elements, and a finite system of equations. Well, m equal 2 is not interesting. Well, it is, but still makes sense, but not interesting. In commutative case, m equal 2 give you just trivial equation, 0, ut equals 0, but in non-commutative not. But m equals 3 already is a quite interesting case. So if you take period of m equals 3, then instead of infinite sequence of equation, you will get only 3 equations on 3 non-commutative variables. Of course, these equations of 3, these 3 equations of 3 non-commutative variables has obvious constant of motion, which is the sum of u. If you take sum of these 3 equations, you will have 0 at the right-hand side, because all terms, cancel off. So we have a constant of motion, and you can reduce all the symmetries for the whole hierarchy, which we have, infinite hierarchy, to this period. And you will get infinite sequence of symmetries on free algebra for this non-abelian system of equation on free algebra. So there is some infinite hierarchy of symmetries. That's what we have on free algebra. Now let us try to quantize this system. To quantize this system, I will use a little bit more general ideal, which still, guarantee the property Q1 that we have additive basis of normal monomials. And that is an example of this G algebra. But not the most general example. Well, that's what I did. So what I do, I say that polynomials now are, when we swap two elements, we have just omega. Now we add to omega also linear term and a constant, and which depends on P and Q. And you think a little bit, and you immediately see that this ideal enable us always to order all monomials, and that algebra has a normal basis of monomials, that is Poincaré-Berghoff-Witt type, and grows exactly like that, non-commutative, everything fine with this algebra. Very good. And that is a G algebra in the terminology of Lewandowski, for instance. So the Q1 is satisfied, no problem. What happens with Q2? Now we need to check. So how many polynomials we have? We have that P more than Q. If m equals 3, so that will be sorry, I will take it off. That will be m. Oh, it will be m minus 1 divided by 2 polynomials which generate our ideal. And we need to check that all these polynomials are invariant. I mean, invariant in the sense, if we differentiate these polynomials, we are still in the ideal generated by these polynomials. So that is a question, and that is a non-commutative computations, which a little bit tedious. So, but you can use now some Mathematica or whatever, or by hand. So Sylvain, Carpentier, everything computed by hand, for instance. Well, if you do that, you will discover m equal 2 is not interesting. We don't talk about that because it's just one equation, basically very simple. M equals 3, you have 3 equations. That's exactly what we discussed before. And we have three polynomials. So n belongs to the cyclic group of three elements. That's three. And all this, they are organized by the same. Instead of, instead of 9 constants, it's supposed to be, because we have 3 values for alpha, 3 values for alpha, 3 values for beta, 3 values for eta. If you do cyclic permutation, it happens that alpha is arbitrary constant, not zero, beta is arbitrary constant, and eta is arbitrary constant. So we have only 3 constants, but they all 3 are arbitrary and admissible, and that is the quotient of our algebra over this ideal is quantization. That is ideal of quantization. If you take m equal 4, a bigger period, then you see that number of polynomials is 6, and they are all here, all 6. And then you will see that well, in this case, the whole ideal is encoded by 3 constants, alpha, beta, and gamma. And in a very peculiar way, that what you can see, that if the neighbors are close, then we have a long expression, like 1, 2, 2, 3, 3, 4. It's a long expression. If we have a gap, that expression is shorter. But that is a result, and that is the only solution for this ideal. So we found the quantization. Moreover, if we take period more than 4, then no these tails, linear or constants, appear. They're all forbidden, and we come back to the same quantization as for an infinite chain. That is an interesting result, I think. Let's look more attentive to the case m equals 3. In the m equals 3, as was stated in this proposition, the ideal generated by 3 polynomials of that form. Cyclic, modulus 3, index n counted modulus 3, and alpha arbitrary constant, not zero, beta is arbitrary constant. Then you can immediately see that if you take h is equal just sum of this u, and we already knew that h used to be a constant of motion for the free algebra, then your equation can be written in the Heisenberg form. Namely, just a commutator of ukt is a commutator of u with uk, and commutation relations are given by this ideal. It's exactly the commutation relations written here, and you can reproduce your system of equations. So your equations has this Heisenberg form in our quantized algebra. Of course, Heisenberg in the sense is in the form, but the commutation relation between u is given by our ideal. What happens with the next symmetry? We know that this equation has infinitely many symmetries. Let's take a next symmetry and do the same reduction, periodic reduction. So I go back, 2 slides, 3 slides. So I take this symmetry, I make a periodic reduction. That means u4 equals u1, etc. So I just make the same reduction for this symmetry. And look what happens. And then I can see that this symmetry is actually not very new. In the commutative case, we know that this symmetry is a 6h multiplied by our flow. But in non-commutative case, this symmetry is also the same flow as here. And if you think that h is a kind of a constant of motion, because it's a Hamiltonian, it doesn't change in time. So it's kind of not a new thing. It's the same symmetry. Moreover, if you look at this algebra and in this algebra, then you can find a Casimir, which comes actually so you can find Casimir, you can find element in the algebra which commute with everything. It's a central element in the algebra. So that is an example of quantization of periodic Volterra system with this arbitrary constants, not one constant, but you have better data, arbitrary, absolutely arbitrary constants you have. And that is a Casimir for this algebra, that is a equation, quantization. You can basically now start to develop real quantum mechanics for this system. Any question at that stage?
No, I think it's clear.
Clear.
To
Am I too slow? Right. Okay, let's go further. Now let's go to Bogoliansky chain. What happens with the Bogoliansky chain when n is not 1? With n is 1, we have, of course, the Volterra system. If n is not 1, what will be the commutation relation? Look, I never appeal to any Hamiltonian structure. To find these things, I don't even use and don't even know whether this equation has any Hamiltonian structure, any Poisson brackets, anything. And I find algebra, I find Heisenberg equation. That is a kind of way how it works. So, a proposition. If you take nonabelian chain, the Bogoliansky chain, this Bogoliansky chain is arbitrary n. We know this integrable system with for arbitrary n is a good system. Now I use the same ideal, I mean the answers for the ideal as I did for Volterra. And what I find out that if the neighboring, if P and Q is less or equal than n, they commute on alpha. Otherwise, they commute. So you write U n plus k equal alpha un plus k un if k less or equal than n. And if k is bigger than n, they just commute. So that fits exactly the case for the Volterra system. So for Volterra system, we know that n equal 1, and that is exactly the answer for Volterra. But if you go further to Bogoliansky, that not just nearest neighbors commute on alpha, but you need to take neighbors up to the n, and they commute to alpha. And if you go further, they just commute. That is a quantization of Bogoliansky. I ask people, well, I asked recently, for instance, Zhenya Sklyanin about quantization of Bogoliansky. He said, no, nobody knows. And if you look on the Hamiltonian, multi-Hamiltonian structure, well, Hamiltonian structure is not so bad for Bogoliansky, at least one. But in non-abelian case, Hamiltonian structure is horrible. There is a recent paper by Matteo Casati and Jinping Wang. They study the Hamiltonian structure for non-abelian Volterra and the non-abelian Bogoliansky chain. And they are really looking horrible. There are no local structures, nothing like that. So if you start from Hamiltonian structure, that could be a problem. But in abelian case, one structure at least very good looking. And this commutation relations really fit very well to this Poisson structure for the abelian Bogoliansky system. Okay, now we have one quantization constant, everything all omega expressed just in terms of one alpha, like we have one Planck constant. Then I did several experiments. I look how this works for several systems. And for instance, you can make some Miura transformation from this Bogoliansky system for n equal 2, and you can find a modified Bogoliansky system with n equal 2. Look, it is n equal 2. It's quite complicated to fourth order in U. U is non-commutative on free algebra system. It is integrable. It has infinitely many flows, etc. but quite complicated. Looking in commutative case, of course, the middle two terms disappear because they cancel each other in commutative case. In non-commutative case, they should stay. Right, and you said the same question. Namely, you use the same J omega ideal, this ideal, and ask the question, what should be omega PQ such that the ideal is invariant with respect to these dynamics? Well, it takes some efforts to solve, and you surprisingly find out that this ideal now depends on two arbitrary constants, alpha and beta. And there is a periodicity modulo 3 in these constants. So now the neighbors very far from each other, not just commute like in Volterra or Bogojevlensky system, but they periodically commute to alpha, commute to beta, or commute to alpha minus 1, beta minus 1. So that is the only solution for this ideal. And that is a quantization which depends on kind of two independent quantum Planck constants or whatever. Usually this alpha beta is some exponential from the quantum Planck constant. So there are two Planck constants, two constants of quantization. That is also kind of a new phenomenon, unknown, and I don't know how to give interpretation of these things. If you go for system with n equals 3, for instance, and make the same, similar modification, then you will get ideal which depends on four arbitrary constants. So there are some quantizations which depend on many arbitrary constants. I did not study this in depth because all these results are quite new, because this kind of quantization I discovered in maybe June, July, and the paper was sent, and unfortunately Sergei Petrovich Novikov communicated to Russian Mathematical Survey. It was published pretty quickly. So, but I didn't have much time to study the quantum mechanics and what can be discovered on this way. But the interesting thing is that it works, and there are cases with several constants of quantization, and you can really, really find these quantization ideals. Now, that is experiment I did recently, and I decide I have maybe 10 minutes. Can I use 10 minutes? Yes? Yes, I see.
Sure you have.
Good. So what I want to do, I want to consider ordinary differential equations on free algebras. And that was a work with Volodya Sokolov, I think in 2000, that is CMP, Communication of Mathematical Physics 2000. We study some kind of equations of ordinary differential equations on free algebras. And this ordinary differential equation, we introduced Hamiltonian structure, all the structure, Lux space, and everything, recursion, everything we could. And also we classified equations of in two variables, u and v, first order equations, like equation 3 here, which have infinitely many symmetries, or which have symmetries, not infinitely many. I will say about that. And for instance, we ask the question, when this equation 3...
sorry, just explain what is the basic algebra. What is K?
K is any arbitrary field of characteristic 0. So you can think that K is Q or Z, or C, Q or C.
Okay.
It's okay. So all coefficients alpha and beta belong, and in the ideal alpha, beta, gamma, delta, eta, all belongs to this field. Let's think about C for, we don't need much from that. So we have equations, and u and v are just elements of free algebra. So any words, different words are different elements. No ordering, you cannot swap anything. That was a setup. And then we ask the questions with Volodya, how to describe all equations of form 3 which possess symmetry of a form 4. So the cubic symmetry equation is quadratic homogeneous. Well, in a sense, you can say that if it is commutative, there is no question about integrability in quadratures, right? Because it's homogeneous equation. Well, it's a first-year student should be able to integrate this equation. Of course, there will be lots of question about, how to make up to implicit function, and well, but nevertheless, it is not a big problem. In nonabelian case, it is no way to do it, but we can ask a reasonable question, because symmetries have a very well defined in non-commutative setup as well, exactly the same definition. So what can we describe all equation 3 which possess symmetry of the form 4? And I ask also a question, what ideals this equation will admit? And the answer is on the next page. So the first, so we discovered that there are 6 equations. Let me do the following. So I will say to the left from here, that's what we discovered with Volodya Sokolov, that there are only 6 equations of this form up to which are not triangular, not, we have some not equivalent, not split, not triangular, just, equations, coupled equations, right? Because we threw away all triangular, all split equations. We use all linear change of variables, everything, and we find that up to these obvious equivalence relations and requirements, any non-triangular system 3 possess non-zero cubic symmetry of the form 4, equivalent to one of the equation from A1 to A6. That is the result. It's in this paper in CMP. Right. Now I ask the question, what the ideals. Now I don't know about any Hamiltonian structure, anything about this equation, but I want to ask the question, what the ideals and what the quantum mechanics can be done with these equations. So what the ideals which satisfy, the ideal which I write obviously satisfy the axiom Q1, so the algebra will be Poincare-Gergov type, and the G algebra has, everything can be done in this case. And I just duly substitute this ideal in the equation, differentiate it, and use modulo as the ideal, try to find 0. And that gives you equations on the coefficients of the ideal. And what you find out, that equation A1 unfortunately cannot be quantized with this type of ideals. Maybe there are some other type of ideals, we don't discuss it, but with this type of ideals, let me remind you what type of ideals. Alpha, beta, gamma, eta. So U, V, V, U. Sorry, alpha, forget. Alpha plus beta U plus gamma V plus eta plus delta U squared. Well, that is ideal generated by this relation. And there are no such ideals which invariant for equation A1. For equation A2, only alpha survive, beta, gamma, delta, eta equal to 0. Then you can immediately find out that Hamiltonian for this equation, the integral, up to this ideal, is alpha u minus v, and you get Hamiltonian equation. U dot equal commutator hu up to some constant, and v dot is commutator hv with the same constant, the proportionality. And same for other systems. Well, I didn't write about A5 because there are some a little bit not so simple picture. Cannot write here in one line. Right. But look, if you look at the last, about the first equation, actually what we also discovered in our paper in CNP, that this equation first, it has only a cubic symmetry in UV, but fails to find any higher symmetry. All other equation has infinite hierarchy of symmetries. So something interesting going on. It cannot be quantized, but it does not have enough symmetries. All other equations can be quantized, and they have infinitely symmetries. Well, if you look at equation A6, which is very good equation, many equations can be derived from equation A6 if you think that U and V are matrices, for instance. It can be quantized, and the quantization, exactly the Heisenberg quantization, so UV swap to VU up to a constant. You can easily check that V cube minus U cube is a Hamiltonian for this equation. So even in classical case, if you consider that U and V are commutative, eta is equal to 0, then H is the first integral for this equation. Having this first integral, you can integrate equation, and if you do that, you will be amazed that solution is given in hypergeometric functions. So solutions quite difficult, but here we have a quantum problem, we have Hamiltonian equation, we find the commutation relation for this equation, so we did a really good step forward. Well, then for completeness, probably I will write another thing, that if you consider equations but which doesn't have cubic symmetry but have symmetry of degree 4, so polynomial, not cubic but a degree 4, then you will find 5 equations. And the same thing works perfectly for these 5 equations. So you can find, so these 5 equations we find on the left, we find with Volodya Sokolov on our paper, and that is if you try these ideals, you will find immediately these ideals, and you find Hamiltonian, and you find Hamiltonian equation, and 6. And that is how Hamiltonian equation looks like for all these equations. So some constants ut is a commutator of hu, constants vt same is a commutator hv, where h is given here for this equation, and these constants k expressed in our quantization constants gamma or eta here. Last equation in this series, last equation, this one, does not have other symmetries. It has only symmetry of order 4 and does not have higher symmetries. So it's not surprisingly that it is not quantized. Equation B4, I don't know why it does not quantize, but it looks like it is linearizable equation, like Burger's equation, by some change of variables, linearizable by non-commutative change of variables. I don't remember that actually. But that is a picture. So what I want to summarize, that look, there is some very simple idea how to quantize equation, and this idea not start from any Hamiltonian picture, not from Poisson brackets, from anything like that, but it starts from opposite end. We start from equations defined on free algebra. Then we try to find a proper invariant ideal in this free algebra and reduce system on a quotient. And this ideal define for us the commutation relation in our system. And we can find Hamiltonian, we can reproduce many things, and that is a very, very simple computation at the end of the story. Of course, lots of things not clear. How to link, for instance, well, I still puzzled what going on with multi-Hamiltonian structure. Is if you have multi-Hamiltonian structure, you're supposed to have many ways, different ways to quantize. Maybe there are some other things. Maybe we need to a little bit to relax our axiom Q1, which is very, very restrictive. That's what I'm thinking. But I still don't have answer to these questions. There are plenty of things about some master symmetries, all this stuff which we learn and develop for integrable systems, how to raise it to this level. Some of them works fine, on free algebra, but we still don't know how to move it to this quantum setup. It's a very, very recent development, and that's what I want to share with you. And if you guys know any, things which been done in this direction, will be very appreciate to get any feedback from you. That's basically everything I want to tell you today.
Well, thank you very much. Well, questions, remarks are welcome.
Вы производные берете по времени, да?
Да.
Does it matter?
Да, конечно, потому что если брать по некоммутативной переменной, то
Ah, you mean, yeah, of course.
Я имею в виду, что у нас есть производная в алгебре, которая определяется вот этим ДДТ. Разумеется, вы должны пользоваться правилом Лейбница, куда там вставлять это юсточкой. То есть нужно делать аккуратно. Вот, но
потому что я работаю в параллельной области. Если вы хотите, я вам могу послать, что у меня сделано. Возможно, сам формат записи гамильтониана, может быть, для вас это будет интересно.
Хорошо. Пришлите.
Я попробую найти ваш email потом. Или, может быть, я свяжусь там.
Email я сейчас вам напишу. Мой email. a.v. Я дам Gmail. У меня есть университет.
Okay.
Gmail.
Я сфотографирую сейчас. Секундочку.
Так что если есть какие-то предложения, замечания, литература, я с удовольствием посмотрю.
Sasha, I have a question. In the end, you said that, well, existence of Hamiltonians may influence the quantization procedure, but your scheme did not use.
No.
What did you mean?
I mean that we have equation on a non-commutative algebra.
Yes.
And this equation, there are some constants. Very often these constants, if you look on this equation, very often this constant give us just a deformation. Like in this equation, like you put gamma or eta equal to 0, you will get just commutative equations.
Exactly.
And that is, what by definition, I have, maybe peculiar definition, but by definition, I want to have equation on the non-commutative algebra. In this algebra, I am able to order the variables so it has a same growth as algebra of polynomials, about the same. Actually, super algebra also will fit this scheme. That maybe, well, I would say that axiom Q1 should be probably a little bit,
modified.
But with time it will modify. But in all known to me cases, it works. But there are some, ideas which require modification. But I'm not ready to discuss these ideas yet. That I would call Hamilton quantization. And if you apply it to all the systems, well, I tried to, for instance, to people study Toda lattice, for instance, quantum theory for Toda lattice. There are plenty of, famous systems which people study in quantum setup, especially the Fadeev group. And these methods give answer in a few lines, all commutation relations. And you don't need to know any Hamiltonian anything. Of course, if you do proper, if you identify things and do proper limit, quasi-classical limit, you will reproduce these Poisson brackets. That is interesting. That is indeed it.
I understand. Okay, more questions, more remarks. Okay, Sash, thank you very much. It was
maybe sorry, I'll have a short question.
Yes,
Does the introduced constructions works for the fields of characteristic 0, or are there some other assumptions about the fields? I mean, those, for example, on this slide we are actually seeing now, there are gamma eta from K, and are there some special assumptions about the field, or we are assuming complex numbers only, or?
No, we don't need characteristic 0 is definitely sufficient. No, there are some, you know, if you consider finite characteristics, so there are some extra problems, which I don't feel myself very confident with finite fields. But I try to look on the situation with finite fields, and I find that there are sometimes you have some problems which disappear in because you know you're working with polynomials. In characteristic 0, you can identify polynomial function and polynomial. In finite characteristic, you cannot, because polynomial may be non-zero and function is 0 identically.
yeah, but in formal computations, it may be not important. Of course, the value of the characteristic may be important in computations, yes, especially in periodic case.
Especially in periodic case, yes.
Yeah. Okay. More remarks?
No, but for instance, I don't assume that what, you know, we have this alpha multiplier sometimes, and people often in quantum, quantum theory assumes this alpha is not a root of unity. For me, it's not important. Alpha could be a root of unity. It does not really play a big role here. And, you know, other structures, like I said, that people study quantum groups, etc., they also can be easily seen as a quotient of the of free algebra of a proper ideal. And this, you know, so that is kind of moving in this direction. And I think these quantum algebras, quantum groups also will play certain roles when we will move to Lax representation, for instance, to psi functions or things like that, or transformations. But that is probably for future. I just try to see how things works in general, and I'm kind of amused and surprised that it works, and it works without this big machinery which people usually use for quantization.
Yeah. Well, it is also interesting how it could be related to Young-Baxter algebras, because that type of non-commutativity.
Right. There are plenty of plans here. You know, that is really very recent thing. It's not just, you know, I was thinking for years. For years, I was thinking that when we did this work with Volodya Sokolov about this nonabelian on free algebras, that time we discussed that, okay, how to do with algebras, you know, with non-commutative algebras, which are not free. And in a sense, we failed that time to find, because I really did not understand that thing that we have to be really work carefully with ideals. And when I realized it, I decided to go from the other side, not to fix the ideal, but to find the ideal. Yep. So the idea is not to fix the ideal, but to find the ideal for a given system.
And this seems to be quite a fruitful. Okay, more questions, more remarks. So thank you very much. And if you have new results, you are always welcome in our seminar. So
thank you.
Just contact me. Thanks a lot.
So I wish you all stay safe and healthy.
Yeah, we'll try, of course. Well, at least as much as we can. Okay, so next time we'll meet again on Wednesday. We shall have a talk by Igor Havkin from Prague. So have a nice week. Goodbye.
Okay, bye-bye.
Have a nice week.
Right.